from Stanford University who will tell us more about block splitting for large-scale distributed learning.
Hi, thanks for having me. So this is joint work with Stephen Pohl. So the problem we're considering is how to decompose learning problems by both features and examples at the same time, potentially. And the problem form we're going to look at is essentially regularized loss minimization. So we're writing it as minimize L of y plus R of x subject to y equals ax. So here A is the feature matrix and x is the parameter vector. And the reason we're writing it in this slightly unusual form is it'll make some of the decomposition stuff easier when we get to that a little later in the talk. We'll see why. And so now we'll consider partitioning AX into NN blocks. So we consider partitioning the feature matrix into potentially uneven blocks of data and features where each aij is an mi, sorry, sure. Where each aij is in mi or mi by nj. And you never actually form this total A matrix. It's just to visualize kind of what's going on. And the idea is to handle each aij separately in the fitting procedure and never transfer it over the network. Now you could also apply this kind of method where either M or N are 1, so you don't necessarily need to split across both data and features, excuse me, but you have that option. Also, it of course applies to cases where you might want to do parallel fitting on a single machine, though the examples I'll be using are distributed in nature. All right, I'll just use this. So the outline is we'll talk about the high-level algorithm that's the basis for the algorithm considered here, then the block splitting method, and then we'll wrap up. So the core algorithm we'll be using is something called the alternating direction method of multipliers, or ADMM. I'm not going to go into motivating how the algorithm works, but we're just going to sort of use it wholesale. So if you consider the generic convex optimization problem, minimize f of z. This is not the same f from before. But minimize f of z subject to z in some convex set C. Then one form of ADMM, which goes under many names, one of which is Douglas-Rackford splitting. It's also a special case of something called a proximal point method. There's many, many other names. Is this one. So essentially it splits into 3 phases. The first one is a prox step, and we'll review exactly what that is in the next slide. There's a prox step. Then there's a Euclidean projection onto the set C, the constraint set C, and then we do a dual update, which is just a vector sum. And I'm not going to go into all the convergence theory, but there'll be a reference at the end if you're interested in that. But basically, it converges under very general conditions, including when f is extended real valued and things like that. You can embed constraints in the domain of f. So the proximal operator, just to review, this is a small typo, this x update, but essentially the proximal operator of the function f with parameter rho, which is a positive constant, positive scalar rather, you minimize f plus this quadratic regularization term, which penalizes deviation from v, where v is the argument. In the rest of the slides, the parameter rho is omitted just to make the notation a little cleaner, but it's in there the entire time. So some special cases that most of you are probably familiar with are if f is the indicator function of a convex set, then the proximal operator reduces to projection onto the set. So you can think of it as a generalized projection. And it shares many properties with projections as well. If f is L1 norm, then this becomes element-wise soft thresholding, which is a very simple operation to evaluate. And if f is this quadratic, then it's element-wise scaling with this multiplicative constant. So it's not going to be the case that you always have an analytical formula for evaluating the prox operator, but it happens reasonably often, and even when that's not the case, it can often be evaluated very efficiently. That's the main takeaway here. So now we'll look at the block splitting method. So the basic approach is we'll take the standard form problem we had before, the regularized loss minimization in that two-variable form with x's and y's. We'll transform it in a certain way. We'll apply this form of ADMM to it. We'll simplify it a little bit, and that'll be the algorithm. So it's not actually a new algorithm. It's just sort of running it on a different problem. Okay, so this is the slightly dense slide. So now assume that the loss function L and the regularization function R are block separable for any kind of blocks, and then the problem becomes this. So in general, we're going to use the index I to index shards of data, and the index j to index shards of variables. So here it's a loss, it's the sum of the losses over chunks of data, and there's m of those, so that's going over block rows, and then summing the regularization function over sets of variables. And many problems can be written in this form, so regularized, generalized linear models, linear support vector machines, and so on. So now what we do is we introduce a lot of additional variables. So essentially just rewrite the problem in higher dimension, I guess. So now we have yi's, which are, again, you can think of those as sort of partial responses for the ith set of examples. Xj's, which is just your parameters for the jth block. And then we also have xij's, which are the ij block's opinion of what xj is, and yiij's, which are sort of the partial responses only using the data aij. And then in order to make the problem equivalent to what we had before, we have to add these two constraints. So we constrain that the xij's over all I are equal to xj. That's a consensus constraint. And then that the yi's sum up in the appropriate way. And then we have that yij is equal to aij xij. You can squint at this a little bit, and it's equivalent to the problem at the top. The point of this is that it'll make the problem split apart. So now what we do is the final step, which is that we move the last constraint, is yij equals aij xij, into the objective, and we just include that as a sum of indicator functions of that set. So now the thing to observe is that the three terms in the objective involve different sets of variables. So the first one involves only yi, then xj, and then xij, sorry. And the two sets of constraints also involve separate sets of variables. So the first set of constraints involves x's, and the second set involves y's, which is what's going to split everything apart. And now we apply the algorithm from before, and we simplify. So for time reasons, I'm not going through the simplification, but this is what you get. And it looks a little complicated, but it isn't so bad. So the first three steps are, again, if you recall, the algorithm had three phases. It was a prox step, a projection, and then a dual update. So the simplest one to see is the dual update. So you've got all of these different variables, and now they're just element-wise sums, so you can write them as three distinct updates here. So you can see those three are the dual updates at the bottom. The top two are the prox function, and that's because the objective has different sets of variables, so you get one prox step for the loss function Li and one prox update for the regularization function Rj, and then the last term here was this indicator, and if you call the prox of an indicator function as a projection, which is where this pi ij comes from. So that's projection onto the constraint set for yij equals aij xij. Then these averaging and exchange operations are projections onto the consensus constraint xij equals xj, and we call an exchange constraint yi is the sum of these yij's. And those are the steps that do the communication. And you can see it's written out here at the bottom that this is what the exchange step is. Averaging is just element-wise averaging. The main point here is just that Collaboration is just involves summing a set of vectors. So that's the part to look at here. I'll leave this up for just a second. But you still would just read this as a three-phase kind of algorithm. Now, just to visualize this as a little cartoon of what the phases of the algorithm look like. So if you picture each of these cells in the grid as being a particular block in that original matrix, and suppose you have a process or thread or machine or whatever handling that, and it's laid out in this sort of grid form, just to visualize it, then the prox steps, the PIJ, and the dual updates don't involve any communication. Those are just handled with each local subsystem. Okay? Then you do this averaging step. That involves sharing information across blocks of data for a given column, so for a given set of variables. So this is, you do big N separate communication steps here in parallel. And then the final thing is the exchange operation, which collaborates across sets of variables, but within each block of data. So you never have sort of diagonal communication or anything like that. The blue dots and the red dots are just X's and Y's, so it's just to emphasize that the consensus is on the X's and the exchange is on the Y's. So in principle, you could actually do the consensus and exchange in parallel also, but that's just a little bit more complicated. So now the one remaining thing that I hadn't described is how to evaluate PIJ. And this actually ends up being the bulk of what you're doing computationally in running this algorithm. So it involves solving this, again, it's a projection onto a constraint of the form y equals ax, and it involves solving a quasi-definite system of this form. Quasi-definite basically means the top left block is positive definite and the bottom right block is negative definite, which is obviously the case here. And one way of solving this is just to give a concrete example, is this thing given here. You wouldn't necessarily do this if A was sparse, but just to take the case where A is dense, you might solve it this way. So an important thing to observe is that this is the only operation in the entire algorithm that actually touches the data. So the prox steps that handle the loss and the regularization don't ever touch the data. It only appears in this. Those are the nonlinearities in the algorithm. The data only ever appears in this linear operator. And the way you would actually implement this is you'd factor, at least if you're using a direct method, which I'll focus on here, you'd factor this matrix A transpose A negative I, or if you did it this way, this I plus A transpose matrix, let's say compute Cholesky factorization of that, that's a somewhat large upfront cost. But then you can cache that factorization and reuse it in all subsequent iterations just using backsolves, which are much cheaper, particularly in the dense case. And we'll see some experiments with that in a second. So here's just an example of what the algorithm looks like for a particular problem. So let's just take the lasso. So here you're minimizing ax minus b squared plus an L1 term. So in the standard form we had before, the loss is quadratic and the regularization is L1. There's a small typo here. It should be lambda over n since you're splitting it into n blocks. But anyway. Then the prox operators are the examples that we saw before. So the quadratic one becomes this multiplicative element-wise scaling on vectors, and the L1 prox is soft thresholding. So those are both very simple vector operations. So you get that the first step is on yi is the element-wise scaling, then you do a soft threshold step, and then the rest of it is the same. So then you do this PIJ projection for all the AIG blocks in parallel, and then you do averaging and so on and so forth. So in general, if you were to derive an instance of this algorithm for whatever problem you're looking at, you basically just have to work out the prox operators of Li and Rj, swap out the first two lines, then the rest of it is the same. So here's a numerical experiment. So here we're just doing it with dense matrices. I mean, you can obviously do everything with the sparse feature matrix, but this is just to emphasize that the scaling doesn't rely on sparsity or anything like that. So each aij is a 3,000 by 5,000 dense matrix. And this solver is written in C, use the MPI for the communication and the GNU scientific library for the linear algebra. And this is all done on Amazon EC2. And we can talk a little bit more about that if anyone is interested. So the computation times, all these times are in seconds. We have 3 scenarios. So one is that we tile these AIJs into a 4x2 system. So we've got 4 blocks of data and 2 blocks of features. Then the second one is 8 blocks of data and 5 blocks of features, and then 8 and 10. So the number of non-zero entries, because the matrices are dense, are 120 million, 600 million, and 1.2 billion here. The number of cores used is 1 per block, essentially, here. So you've got 8, 40, and 80. The factorization time is all completely in parallel. So that's the same regardless of how large your problem is. So that takes 15 seconds in this case. So that's a one-time cost again. Then you cache that. All the subsequent iterations take around 1/10 of a second to actually carry out. And these problems didn't get large enough where the communication started to degrade the speed, but I mean here they stay pretty much constant. The total number of iterations you end up running in these cases are 90, 230, and 490, which seems like a substantial increase, but if you look at the actual amount of wall clock time it takes to run the main loop, excluding the initial factorization, it's 10 seconds, 27 seconds, and 60 seconds, respectively, which gives a total time of 28, 50, and 80 if you add in time for data loading and stuff like that. So just a couple of observations. In many but not all cases, evaluating this PIJ operator is the majority of the work you're actually carrying out. You can get large speedups via this factorization caching trick. And if you were using an iterative method to solve that linear system, then you could warm start it, and there's other tricks that you can use there. All the communication involves summing up a bunch of vectors, right? Because you've got an averaging step that's just summing. And then the exchange, the collaborative part of that was also summing. So you can do everything via all reduce operations or equivalent in whatever programming framework you're using. So MPI has an all reduce. Valpal Wabbit has a Hadoop compatible all reduce. And any of those would be fine. And again, to emphasize this sort of unusual aspect of the algorithm, it splits apart the nonlinear parts, which is the objective, and the data, which is handled using this linear operator. And not that there's necessarily any point in doing this, but you could, in principle, fit multiple models simultaneously, right? Because the factorization that you cache is the same regardless of what model you're actually fitting. So another way to think of it might be as, in analogy with sufficient statistics or something, it's like a sufficient operator. You could chuck the data after doing that initial factorization cache and then just reuse it whenever, regardless of whatever you're doing. And anyway, that's basically it. The method basically coordinates a bunch of processors, each solving a small convex optimization problem to solve a larger problem. You can split by data, features, or both. The algorithms are quite easy to implement in general. That's basically it. Here are some references. There's the workshop paper, then there's a longer paper on ADMM for distributed optimization that doesn't include the sort of two-way splitting case that has a lot more background on the algorithm itself if you're interested. And it's available from either Stephen Boyd's site or my site. And any questions, I guess?
Because I knew that ADM is only version for two layers, now we have many layers.
No, well, not exactly, because it's the same algorithm, right? It's more like one variable, we're calling the variable z a stacked version of x and y and all that stuff. So the same two-variable ADMM algorithm is what is being used here. It just takes this other form because of replicating a lot of variables. So all the same convergence results hold.
Can you go back to the factorization slide?
Sure.
This is done for each subblock, right?
Yes.
For the small block, and it is done locally on the
Yes.
clusters.
Yes. So, I mean, it's privacy preserving and all that too. Each AIJ is just on its own block. I mean, how you split up your overall matrix that you never form into the AIJ is not considered here. You might have it already stored in a split form, or you might have might be something on the problem that tells you how to split it. For example, if your regularization is group lasso, that's you're regularizing chunks of variables, that would be a natural way to split it up by features.
So the regularization parameter never appears in that.
No,
What
no.
you mentioned about multiple model.
No. It does not.
So this one factorization is not for all lambdas.
Yes, yes. So, for instance, if you wanted to compute the whole regularization tab, say like 30 different lambdas, if you're doing a lasso or whatever, then this work is over.
I was going to keep you up on the podium a little longer. So you mentioned that on the last slide that most of the work happens during this projection step, where you tie together the two the y's and the x's and then you do this solve this and everything. So and you had this really interesting idea about, well, because the method also separates out the data from the model fitting part. Try out multiple models for the same sort of statistics. Can you elaborate on that? And any plan? It sounds very interesting. Do you guys plan to pursue that direction? What exactly
Not. There's nothing in particular to pursue, I think. So the PyIJs are the bulk of the work when the prox operators are simple. So for things like the lasso, that's the case. If you're doing some much more complicated problem, it's possible the proxies are not completely trivial. But for these kinds of cases, they are. Now, I mean, this thing of fitting multiple models at the same time, I mean, that would really be application dependent. We're not looking at any particular case where that's important, but I mean, if you wanted to fit, let's say, you're doing some classification problem, you wanted to fit logistic regression and SVM and compare them, or you wanted to fit logistic L1 regularized logistic regression with a whole bunch of different lambdas, then you could fit that in aggregate much more quickly. So this is, I don't know what the follow-up would be there, but
right. So this step is also the synchronization step, right? So you
no, not this one. This one is completely separate.
Oh.
So this one happens, yeah, so this, again, going to this cartoon, the PyIJs in here, so each guy does this heavy lifting in parallel by itself with no communication. The communication is just element-wise vector sums, and there you're doing these yi's and xj's and adding them up, basically.
Is there any way to make use of sparsity? You work with dense A, but if for sparseness, do you get any additional benefit? Sparsity?
Not necessarily an additional benefit, but you'd also get a benefit. I mean, there you probably wouldn't solve it this way because you don't want to form as A transpose, but there are pretty good direct methods for solving that quasi-definite system at the top. Like we've taken LEL transpose factorization and then catch that and then back solve it. And if the whole matrix is block sparse, I mean, you'd also get, I mean, there is an additional benefit you get from sparsity where it's possible an entire AIJ is 0 and it would just drop out of the computation entirely. So you would get some benefit there.
Just for clarification, your A is actually the data, right? What
Yes.
you call X usually in machine learning.
Yes.
So yeah, you change the notation somewhat.
Yes, yes. Yeah, the A is the feature.
pleasure for me to get a tattoo.